Professor Hilliard, Professor Constantopoulos, Professor Liu, and Professor O'Reilly. Thank you for taking the time to watch this demo. My name is T. Chan. I am a Master of Science in Software Engineering Systems student at Northeastern University's College of Engineering. This video is a walkthrough of my thesis project, DataLens, an interactive platform for protein mutation analysis. When you first open DataLens, you are greeted by a welcome modal. This introduction panel explains the tool's purpose and includes a disclaimer. DataLens is a research triage tool. It is not a clinical diagnostic system. Every result you see in this demo is intended to support exploratory analysis, not to replace expert biological judgment. You will also notice the AI Assistant panel on the right side of the screen. This panel maintains a full conversation history across your session, so every query, response, and insight is preserved as you move through your analysis. Let's load our first protein. I'm fetching BRCA1 from the RCSB Protein Data Bank, PDB entry 1T29. DataLens sends an HTTP request directly to RCSB and parses the PDB file in real time. In a moment, the protein appears in the 3D viewport, rendered as a ball and stick model using instanced OpenGL rendering with the protein loaded. Let's look at the mutation landscape window. This panel visualizes the alpha-missense pathogenicity landscape for this protein, covering 59,128 variants across 1,863 residue positions, pulled instantly from our PostgreSQL database of over 216 million pre-computed predictions. Each cell in the heat map represents one residue position. What the mutation landscape panel displays is the worst-case substitution at that position, the single amino acid change with the highest pathogenicity score. So if residue 987 is an arginine, and mutating it to aspartate scores higher than any other substitution there, that aspartate variant is what you see in the landscape. This gives you an immediate triage signal, which positions are most dangerous to touch at all, before you drill into the specific substitution. Each cell in the heat map represents one possible amino acid substitution at one position. The color encodes predicted pathogenicity. As I hover my mouse across the landscape, cells highlight in cyan, that's hover mode. When I click to select a variant, the cell turns orange, that's selected mode. Notice that in the 3D viewer, the corresponding residue simultaneously lights up in orange. The 3D structure and the mutation landscape are fully linked. Let me rotate the model so you can appreciate the 3D structure. The molecule rotates smoothly in real time. This is powered by instanced rendering. 2 draw calls render the entire molecule, whether it has 500 atoms or 50,000. Now, let me direct your attention to the variant selector panel. This window gives you full manual control. You can browse all 1,863 residue positions, and for any position, manually select which amino acid you want to mutate to. It's the interface between the mutation landscape and the structural viewer, giving you precise, reproducible control over your analysis. Let me click on a few mutations in the landscape. Each click selects a variant. The affected atoms in the 3D view immediately highlight in orange, showing you exactly which region of the protein this substitution touches. I can click through several nearby mutations rapidly, building an intuitive sense of which structural regions are most vulnerable to amino acid changes. Now let me walk through a focused mutation analysis. I'm going to select residue 1706 using the selection command, R equals 1706. The corresponding atom highlights in orange in the 3D view. Residue 1706 is a glycine, a small, highly flexible amino acid that plays an important role in maintaining local backbone geometry. In the variant selector, I navigate to position 1706 and choose to mutate to E, glutamic acid, also called glutamate. Now I click Run Folks. A mutation focus panel appears. It summarizes the key structural change: wild type, glycine, small and flexible, mutant, glutamic acid, negatively charged. This is a significant physicochemical shift. Glycine is the only amino acid without a side chain, giving it exceptional conformational freedom. Replacing it with a bulky, negatively charged residue introduces steric constraints and electrostatic effects that may disrupt local structure. While we wait for the backend to return the Folks result, you can see the frame counter in the corner of the screen. DataLens is maintaining smooth rendering throughout the computation. The mutant structure has arrived from the backend API. The mutant viewer panel is now open. It uses a 3-color encoding: orange atoms, lost, These atoms are present in the wild type but absent or displaced in the mutant. Blue atoms, shared. These atoms are structurally conserved between wild type and mutant. Magenta atoms, gained. These atoms appear in the mutant but not in the wild type. Let me switch into mutant viewing mode. As I rotate the model, all other residues across the protein are dimmed to gray. Only the affected region remains in full color. This visual dimming is intentional. It directs your attention precisely to what changed, without the noise of the surrounding structure. Now switching to wild type mode. The wild type atom appears in orange, the mutant in gray. You can see directly what has been lost and what has been gained between the two conformations. Now let's consult the AI assistant. I'm fetching additional context from the UniProt knowledge base for this residue, and submitting a query about this specific mutation to the Claude API. The AI synthesizes a response drawing from multiple sources simultaneously. ClinVar clinical classifications, UniProt functional annotations, NOMAD population frequency data, fold stability predictions, and alpha-missense pathogenicity scores. The response explains the likely mechanism of disruption, characterizes the structural impact, and provides a confidence assessment based on the agreement across these independent data sources. And at the end of every AI response, DataLens always displays the following disclaimer: for research use only. Do not use for clinical or diagnostic decisions. This is DataLens, a fragmented multi-tool workflow collapsed into a single interactive environment. Triage that once took 10 minutes per variant now reduced to no more than 2 minutes. Professor Hilliard, and members of the committee, thank you again for your time, your guidance, and your support throughout this project. I look forward to our discussion on April 20th.